Today we're going to be looking at another Nilered video, specifically making an atomic trampoline. Insanely bouncy. I have to say the title alone got my attention. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer, a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's check this out.
This video has been sponsored by Opera. It was almost 2 years ago when I saw this video by Steve Mould, where he showed something that I'd never seen before, called the atomic trampoline. He also showed how it worked by just getting a regular ball bearing and by dropping it from about 1.5 feet. And honestly, it was pretty lame. I'm just kidding though, and that was exactly what he expected to happen. And this was because this cylinder was just made of some generic stainless steel. This, on the other hand, was the actual atomic trampoline, and for the most part, it was basically the same thing. However, what made it a lot more interesting was that it had this extra layer of special metal on top, and when he dropped the ball onto it,
Special metal.
the difference was almost unbelievable. It just kept on bouncing, almost like it was never going to stop, and it just didn't make sense to me how this kind of generic-looking piece of metal was able to make such a huge difference.
That's cool. First, I'm going to say atomic trampoline, not a standard nuclear engineering term. At least not one that I've ever worked with. What we're looking at here is merely a trampoline bouncing analogy used to visualize energy states and transitions. So the ball is the particle jumping, bouncing off of a barrier. When it gains kinetic energy, when it moves towards the trampoline, it bounces back to a corresponding energy level. So you can use this as an analogy to see how particles behave in energy wells. At least that's what I think this is supposed to visualize. It's not using an atomic weapon to bounce something really high into the air. That's the topic for a different video.
Steve quickly cleared up a lot of this confusion though by explaining that it was made using a relatively new and unique type of material called amorphous metal or metallic glass, which was very different than normal metal.
Interesting. So amorphous metals, unlike the typical crystalline structure you see in metals, have a disordered structure kind of like glass. I've also heard them referred to as metallic glass. They have higher strength and hardness, they have magnetic properties, and they're more resistant to corrosion, though they are more expensive to manufacture. I've seen these used in transformers, and because of their unique properties, they make transformers way more efficient. Now the trade-off is it's more expensive to fabricate amorphous metals, but they pay for themselves in the long run. Kind of like when LED light bulbs were first introduced, how they were more expensive than regular incandescent bulbs. But yeah, amorphous metal transformers, higher energy efficiency. They can also operate at lower temperatures to receive the same level of electrical output because amorphous metals have less heat losses than a traditional transformer that has a steel core, for instance. But they're pretty cool. They're also used in high-end golf clubs because of their extra bounciness to get you to drive the ball farther, though I don't claim to be an expert at golf.
He then went on to talk a lot more about it and why it was so bouncy, but the whole time, the only thing that I could think of was that I really wanted to buy one of these atomic trampolines. The only problem was that according to Steve and hours of my own research, a setup like this was now impossible to buy, and Steve was only able to get this one by borrowing it from another channel called Grand Illusions.
I wonder why it's impossible to buy now. Shortage? When
I found this out, I was honestly pretty disappointed, and I still don't really know why nobody makes them anymore. What I do know, though, is that not being able to buy one kind of made me want one even more. And at this point, it was pretty clear that there was only going to be one way for me to get an atomic trampoline.
Here it comes.
And I was going to have to try and make one myself. The only tricky part was that I still didn't entirely know what metallic glass was, and I definitely had absolutely no idea how to make it.
Okay, so he is using amorphous metal and metallic glass interchangeably.
But for some reason, I felt that I could do it, and I decided to just go for it. So I just jumped right into working on it, and I felt that the best and most important first step was to figure out how a disc of metallic glass is typically made.
That's always a good first step in any project, to figure out how to do it. Actually, that's not true. The best step is probably to figure out if it's a good idea to do it. Look at all the implications of what it would be like to manufacture something like that.
However, even after hours of searching on Google and reading anything that seemed remotely relevant, I wasn't able to find much of anything. This is because, as far as I could tell, there was basically no information about specifically making a disc, and I was only able to find generic industrial methods that showed how to make things like ribbon. On the bright side, though, all of this research still wasn't a complete waste of time, because I was able to find a lot of interesting information.
Going deep down the material science rabbit hole, I see.
About metallic glass in general. For example, there are apparently an insane number of metallic glasses where each of them have completely different compositions, and they all vary in their physical properties like density, elasticity, and hardness.
Pick one.
This also meant that they all likely varied in their level of bounciness, and because of this, I almost definitely couldn't just make a disc of it using the easiest recipe that I could find. In my mind, if I wanted it to bounce just as well as it did in the video, I was gonna have to make the exact same metallic glass.
How do you know you can't make one that's, like, maybe there's a reason why he made one with that level of bounciness and not so crazy bouncy that it's atomic flubber?
So I went back to Steve's video, and this time I listened to it much more carefully, and it was around the 7-minute mark that he thankfully said exactly what it was made of, and that it contained
zirconium, beryllium, titanium, copper, and nickel.
Interesting combination. Also interesting that he mentioned beryllium, which is toxic, both as a skin irritant, toxic, and an inhalation hazard. At 4 milligrams per cubic meter, you're at the IDLH threshold, or immediately dangerous to life and health, with workplace exposure limits of less than 1/1000th of that. So, not saying you can't try to make that, but just be careful. From what I've seen of Nilered in the past, he follows good chemical lab safety procedures, so as long as he treats it with the respect it deserves, he'll be fine.
With a bit more research, I was then able to find that this composition in particular was called Vitrolloy 1, and it was actually one of the first commercially viable and mass-produced metallic glasses. Its exact composition was also conveniently listed on Wikipedia, and it was apparently 41.2% zirconium, 22.5% beryllium, 13.8% titanium, 12.5% copper, and 10% nickel. At this point, I now knew exactly what I had to make.
Of that alloy, beryllium definitely fits the category of one of these. It's not like the others.
Which I felt was some good progress, but what was honestly kind of scaring me was the fact that it contained beryllium. This is because in general, beryllium is known to be toxic and horrible, and when I looked it up, it said that breathing in its dust or fumes could cause permanent scars to develop in the lungs. This in turn could then apparently...
This isn't radioactive, but as far as the contamination procedures he'd work with, this would be, you would have to handle this with the same level of strictness as something that's highly contaminated. So protective clothing, coveralls, gloves, mask, because it's also an inhalation hazard. I can see why this scares him. I wouldn't want to work with this either.
Lead to something called chronic beryllium disease, or beryliosis, which is an incurable and potentially fatal lung disease. It really sounded like it was basically just the asbestos of metals, and what made it even worse was that apparently just one single exposure could potentially lead to beryliosis.
4 milligrams per cubic meter is not very much. I've never worked with beryllium like this, but I do know IDLH procedures usually involve wearing SCBA. IDLH atmospheres usually involve wearing SCBA. Not saying he needs to wear one for this experiment, but I just know it's taken very seriously.
Overall, this all honestly sounded pretty terrifying, and at first, it kind of made me want to just abandon the entire project.
I like the little stars.
However, after thinking about it for a while, and reading a lot of stuff about beryllium in general, I started thinking that it was actually possible for me to work with it safely, and I would just have to follow two very important rules. Number 1, make as little beryllium dust and vapor as possible. And number 2, absolutely don't breathe in any of it.
I like he intentionally memed it. Don't breath any of it. Also, you don't want to touch it with your bare hands either.
In general, Rule 2 was actually relatively easy, and all I needed was some good ventilation and maybe a mask. But Rule 1 was a bit trickier, and it would severely limit the ways that I could make the disc. This is because minimizing dust would mean that I wouldn't be able to shape the metallic glass like normal metal by grinding, cutting, or machining it, and instead, I was gonna have to somehow directly make pretty much the exact disc that I wanted. In my mind, this left me with only one real way, which would be to melt all of the ingredients together and to pour them into some sort of mold, and at first, this seemed relatively simple. However,
immediate challenge coming to mind is just avoiding contaminants in the mold, especially if you only have one shot at this.
When I looked into things a bit more, I realized that there were a couple small details that were gonna make this process way more difficult. The first was that all of the ingredients were sensitive to oxygen, and this meant that I could only melt them with absolutely no air present. Then the second was that to form metallic glass, the molten metal had to be cooled as fast as possible, and this meant that the mold that I used had to have some sort of cooling system. Altogether, this definitely wasn't ideal, but I still felt that it was doable, and at this point, I was fully committed to the project. So I immediately dove right into planning it, and the first thing that I did was reach out to Steve Mold to get the exact dimensions of his disc, and he was nice enough to help me out. I then spent the next few weeks trying to come up with a setup that I thought would work, and my first idea was to do something similar to when I made purple gold.
Yeah, this is
because to do that, all I needed was a simple furnace with a crucible, and with a small tube shooting in some inert argon gas, I was able to easily protect all of the molten metal from air. I was also able to quickly pour it all out into a graphite mold, and even though it was extremely reactive, it only seemed to get slightly oxidized on the surface. In my mind, this basically solved pretty much my entire problem with air, and I figured that for the cooling part, the only thing that I would have to do differently was pour it into a perfectly sized little disc mold, and to quickly cool it using something like a computer heatsink. What was also nice, and
that's cool, just copper, though I've never seen any computer reach melting point temperature, so we'll see if this is enough.
And extremely important was that it was very easy for me to do all of this in one of my fume hoods, which would completely protect me from the scary beryllium. Overall,
So beryllium in nuclear engineering, you'll see it as a neutron reflector in certain types of nuclear reactor designs and also in nuclear weapons. And what it does, by reflector, I mean it scatters neutrons in a way that they do not escape the reactor. It reflects them back in. Water also has similar properties in a pressurized water reactor, but for something really compact, especially like a weapon, water's not very space effective. And beryllium is good because it has a low atomic number, that of 4, and there's also a very low chance for it absorbing neutrons, so it's much more likely to scatter them back into the reactor. That also makes it good as a neutron shield because, again, it's going to scatter them, and the neutrons, when they're scattered, are going to go backwards. They're going to lose a lot of energy, so it can make effective shielding in that regard. I will emphasize in both of these environments, a nuclear reactor, ultra high temperature, ultra high pressure, and a nuclear weapon, I shouldn't have to explain that one, are not environments where you're going to be around, where you are going to be close to them. Reactors have multiple walls, multiple layers of containment made out of multiple feet of concrete. So you're very far away from the toxic source of beryllium as well as the high heat, high pressure, and high radiation of a nuclear reactor. It can also be used in fusion reactors, tokamak-style reactors, and again, it's neutron shielding because fusion reactions do also release neutrons. Not to mention limit the release of impurities into the plasma in the case of fusion. So Beryllium comes up quite a bit, but I've never personally made anything out of it.
Really felt that this solved pretty much all of my issues, and I was actually very close to testing it out until I randomly stumbled onto this paper that I'd somehow never seen before, which explicitly talked about making discs of metallic glass. They also included a photo of something that they made, and it was pretty much exactly what I wanted, and what was especially nice was that they explained exactly how they did it. Specifically, they said that all of the ingredients were arc melted together and then suction cast using water-cooled copper molds under a purified argon atmosphere.
Okay.
At first, a lot of these words, honestly,
argon's good at purification because it's inert, just like any other noble gas.
Didn't mean very much to me, but with a bit more searching, I found that at least on a lab scale, this seemed to be a somewhat common way to make metallic glass. It also seemed like the main part of the setup was this thing called an arc melter, and with even more searching on Google, I was able to find a bunch of photos. I then took a closer look at what appeared to be the simplest one, except what kind of concerned me was that I honestly had no idea what I was looking at. After examining it a bit more, though, I realized that it was actually a lot simpler than I thought, and it was basically just a standard welding setup with some extra parts. This was especially highlighted by the fact that it was powered by a common welding power supply, and that the positive output was connected to a standard tungsten welding electrode.
Welding is such an underrated trade I've seen, but is highly, highly sought after and lucrative. It seems like there's just, I remember during an outage needing to bring in specialized welders that are not only expert level or master level, whatever the highest skill level is, but also just experience working in nuclear power plants. So having those specific skills and experiences, they're just difficult to come by. For whatever reason, welding isn't like promoted as much compared to engineers. We were even in a situation where we had more nuclear and mechanical and material engineers on site than we did welders. So we had to bring in some specialized contractors, and they were not cheap. So definitely a lot of money to be made with being a good welder, and not just in the nuclear industry. It's a very, very underrated skill.
There are of course some major differences though, and the first was that the other wire, which is normally attached to the thing that's getting welded, was instead attached to a water-cooled copper crucible.
Interesting.
Then on top of this, all of it was enclosed in a glass or metal shell and filled with an inert gas like argon, which would completely protect it from air. With this setup, it was also apparently possible to liquefy almost any metal, and I found this really cool demo of one on YouTube. The moment that it was turned on, it immediately released some blindingly bright light, and this is because a plasma was being generated.
Plus, you get to work with plasma as a welder. That's the other cool thing.
Between the electrode and the copper crucible. This plasma was then so hot that it was able to almost instantly liquefy any metal that it touched, and it honestly kind of blew my mind how fast it was able to melt it.
It's powerful.
With that being said though, after seeing this, I almost immediately wanted one, mostly because it looked really cool, but also because it really did seem like an arc melter would be both the easiest and safest way to work with the metallic glass.
Plus, he'll have it around and be able to use it for future videos. I like that. I've watched several of these Nilered videos now. He's slowly adding to his shop of, at least to someone like me, a bunch of exotic tools. Now, they might not be that exotic to some people, but he's amassing quite a collection, so he's getting to where he could make just about anything, which is pretty cool.
What I also think made it even more enticing was that with a slightly larger one like this, it was apparently possible to incorporate a custom mold into the water-cooled copper crucible.
More
this
versatility.
would then allow me to directly suction cast the molten metal into the exact disc that I wanted, and at the same time, it would also cool it extremely quickly, which was very important, and at this point, I was pretty much fully committed to getting an arc melter. The only problem was that just by looking at it, I knew that it was going to be expensive, and after talking to someone on Alibaba for over a week, the final quote that I got was $14,000. This was way more than the close to $0 that I would have had to spend on my other setup, and the number honestly kind of shocked me. It was clearly the much better and safer option, though, yeah. And on top of this, they
containment is expensive.
Confirmed that it was no problem to make a disc mold with the exact dimensions that Steve had given me. So I decided to just go for it, and after a few months of patiently waiting, I eventually received this large wooden box. I then spent the next 15 minutes taking everything apart, and I got rid of all the packaging, and I was very happy to see that I now had everything that I needed. More specifically, I had the power supply, a water chiller, and a vacuum pump, and of course, the space-age looking arc melter. Now, all I had to do was put it all together by first plugging in the wires from the electrode and the crucible to the power supply, then by connecting the chiller to all of the blue water lines, and lastly, by attaching the vacuum pump to this little pipe sticking out on the side.
Vacuum pump would also be useful in reducing contaminants, non-condensable gases, that sort of thing. At nuclear power plants, we use them in the secondary side, the non-nuclear part of the plant, the main condenser. It not only improves water chemistry, the condenser at a near vacuum greatly boosts thermal efficiency of the entire nuclear power plant. And there's nothing nuclear about that process. It's the same steam cycle efficiency process that you would see in a coal or a natural gas.
I also went and got my argon tank, and I attached it to this part at the top, and when I was done, I felt that it was looking pretty good. I then opened it up to check out the copper crucible, and I was really happy to see that it was exactly what I had asked for. In the middle, there was the custom mold, which I will talk more about later, and around it, there were 4 small rounded wells, which I could use to melt metal. There were also 2 custom ones with an exact diameter of 44 millimeters, and I had made these just in case the mold somehow totally failed.
It's good to have contingencies.
This way, I would at least have something to potentially fall back on, and like the mold, I'll talk more about them later on. Either way, with it all assembled, it was finally time to test it out, and I was pretty excited. I was also kind of tempted to just immediately try making some metallic glass, but at the same time, I knew that it was an absolutely horrible idea.
Start with beryllium. Faster results, question mark. Cons, I might die. I love these little slides he puts in.
Idea to do my first attempt with beryllium. I mean, it definitely made a lot more sense to first actually learn how to use it before working with something dangerous.
Just test.
So instead, I decided to start out with some iron.
I like that it's not right next to his radioactive material drawer that I saw him use in the uranium glass video.
Which I felt would be similar to the metallic glass because it would also have a high melting point, and when it was molten, it would be sensitive to air. I also just happened to have all of this high purity iron, which was perfect for this, and I loaded up one of the small wells.
I love the sound of that.
I then lowered down the main chamber, and I clamped it shut, and I turned on the vacuum pump to pull out all of the air. To monitor this, I just looked at the pressure gauge, and when I have
That's good. It just says megapascals, despite the rest of it not being in English, which is good to know. I'm glad most countries, looking at you, America, have agreed on a system of units. Also, he's not having lower pressure than absolute zero. This is just what you see on a pressure gauge, which is relative to atmospheric pressure. So, no violation of the third law of thermodynamics is occurring, as far as I can tell anyway.
Eventually saw that it stopped going down. I closed the vacuum, and I opened the valve to the argon. This caused the argon gas to rush in and for the pressure to increase again, and when it eventually got back to around 0, I turned off the gas, and I flipped back on the vacuum. I then repeated this exact same process 3 more times, and when I was done, I closed both the vacuum and the argon valve. All of these cyclings should have then left me with a chamber that had effectively no oxygen or moisture in it, and only inert argon, and I was nearly ready to start blasting the iron. The only thing left to do was to flip on the power supply and to quickly do a horrible job setting up a camera to look inside, and at this point, I just had to click the pedal on the floor to make it go. So I quickly lined up the electrode above the iron, and I was honestly a bit nervous, but I just went ahead and clicked it, and the whole thing immediately lit up. Within a fraction of a second, the argon between the electrode and the crucible had been turned into a plasma, and I don't know why I was so surprised that it was working.
Really.
It's working! The only problem was that it seemed to be struggling to melt the iron, and this was because the power supply was still at its lowest setting.
Okay.
I started it like this because I wanted to start safe.
Of course.
But clearly it needed more power to generate a hotter plasma, and I quickly ramped it up. As I did this, it immediately got a lot brighter, and not long after, there was thankfully some molten iron. This was actually really impressive,
That's awesome.
Considering that iron melts at around 1500 C or 2800 Fahrenheit.
That's hot.
And to do this in seconds was kind of insane. What I thought was even more impressive, though, was that in less than a minute later, it had completely liquefied, and I had an absolutely ripping...
Well, arc welding can get over 5,000 degrees Celsius, and then you have plasma torches, which are upwards of 25,000 Celsius, so we're talking far hotter than the surface of the sun. But nothing close to the core or the corona for that matter, which is interesting. A lot of people make comparisons to the surface of the sun.
Hot blob of iron. It also didn't seem to have any oxides forming, which told me that the inert atmosphere was working, and overall, I was very happy with my purchase.
It's beautiful.
I mean, it really was just as cool as I had imagined, and even if I completely failed to make the metallic glass, I had absolutely no regrets.
Yeah, but you got a new cool toy.
That's really cool.
Yeah.
But with that being said, the iron wasn't going to get any more liquidy, so I stopped blasting it, and I let it cool down. Then, several minutes later, when I felt that it was ready, I popped open the chamber, and I saw my beautiful little blob of iron metal.
Nice.
I was also really happy to see that it didn't look like it got oxidized at all, but it was surrounded by a bunch of black junk, which I think is just carbon. I then took a closer look at it, and when I flipped it over, I noticed that the bottom side wasn't properly melted. I really thought that I had avoided this by absolutely blasting it, but clearly the cold copper really did its job, and the stuff at the bottom would probably always struggle to melt. But moving on, the machine clearly worked, and now, the only other thing that I had to do before working with the scary beryllium was test the mold.
Yes.
Up until now, I'm assuming
he's tested all of his immediate... And I'm glad he brought up the fume hood, he brought up safety equipment, minimizing dust, essentially good housekeeping before messing with the beryllium.
Never explained how this mold even worked, but thankfully, it was supposed to be pretty simple. The basic idea was that the mold itself was made from two separate pieces that were just sitting snugly in the crucible, and between these two pieces, there was a cavity in the shape of a disc, which had a diameter of exactly 44 millimeters and a width of 3.5 millimeters. Then, according to the manual, to fill this with metal, all I had to do was melt some metal on top of the mold, which apparently wouldn't fall through the hole, until I opened the vacuum valve. This was then supposed to pull a vacuum through the hole in the bottom, which would cause the metal on the top to get quickly sucked in, and once it was full, the cold crucible would cause it to almost instantly freeze.
That is cool. Seeing this reminds me of an entirely passive safety system in a molten salt nuclear reactor, one of the advanced designs. You have a freeze plug down below in the reactor's drain pipe. It's a solid plug of salt that is continuously cooled with a refrigeration system. Normally, the cooling system keeps it shut, so the salt just goes through the chemical processing plant and circulates back in through the reactor during normal operation. But if the reactor were to overheat, or the refrigeration system fails, the cooling system shut down, the freeze plug melts, all the fuel is dumped into the emergency tanks, and the reactor is safely shut down and cooled down. It's entirely passive because gravity's not going to fail on you, and the idea of hot things melting cold things isn't going to fail on you. That's just what that little thing reminded me of.
After that, I just had to pull the entire mold out of the crucible and open the two halves, and this would leave me with, at least theoretically, a near-perfect disc of metal. In my mind, this all seemed relatively simple.
Really fancy, bouncy hockey puck.
And straightforward, and to get things going, I just loaded a bunch more iron onto the mold. I then sealed the chamber and cycled it like before, and I blasted it until it was completely molten. Now, to turn this red-hot metal into a hopefully beautiful disc, I apparently just had to quickly open this valve on the side and pull a vacuum. I then expected to see all of the metal to just quickly get sucked into the mold, except, well, absolutely nothing happened. It just sat there with seemingly no intention of going into the hole, even with the vacuum on full blast. I then spent the next several minutes trying a bunch of different things to make it work, like increasing the power and blasting it directly in the center above the hole, but it didn't seem to make a difference. I also tried it again using a lot less iron, and I heated it for a lot longer, which I was hoping would help it melt at the bottom and magically fix everything.
If only you could somehow just heat it from all sides and put torches or a perfectly spherical heating element. That'd be a lot more expensive than $14,000, I'll tell you that. That's also why we don't have spherical nuclear reactors. They are quite impractical.
Except that still totally failed. So using this mold apparently wasn't quite as easy as I assumed, and in a desperate attempt to figure out what was going on, I ended up spending the next few days trying a bunch of random things. I also ended up trying it with lower melting point metals like aluminum and tin.
Beads of tin, I like that.
If that would make a difference, and with those, I was actually able to get some to go into the mold, but the result was always trash. Many more repeated failures then eventually pushed me to the point where I started thinking that there was actually something wrong with the mold. Why didn't it all just suck in? And I was honestly getting pretty close to just giving up. Thinking that this is just not the way to do it. However, I then decided to try it one last time, doing something different, and I'm really glad that I did.
I'm glad he shows us all the intermediate steps of things that didn't work, and even some of the results that weren't as desirable. Because you see on so many of these sorts of videos, they just show you, oh, it worked perfectly, like it was the first attempt, when, nah. There's a whole bunch of trial and error, and I'm assuming way more that he's not even showing us when he goes through all of these processes. The idea of doing anything from scratch with very limited instructions and procedures is honestly quite impressive. I'm so used to being in the nuclear industry where a procedure is prepared, reviewed, goes through a big review committee, and you have so much empirical operational data to go with that it's shared before you even take pen to paper to write said procedure. So what Nilered is doing is both parts impressive and scary. So I just appreciate that.
Because to my surprise, it actually seemed to work. Almost all of the metal was sucked into the mold, and when I popped it out and opened it up, I was shocked to see a nearly perfect disc. Oh my god. It worked!
Like the dramatic pauses.
That's perfect. It's actually perfect.
Nice.
It's a nice little disc. Wow. I then attempted it a couple more times, doing the exact same thing to make sure that it wasn't just a fluke.
Getting repeatable results is good.
This, of course, told me that the mold wasn't broken or something, and it was kind of just poorly designed and super finicky. What I mean by this is that for it to work, I found that I had to use a specific amount of metal, heat it for a certain amount of time, and open the vacuum valve at a particular speed. If I didn't do all three of these things properly, it would usually fail, where the metal would either refuse to go in, or only a very small amount.
You see, in the procedures I'm used to, it specify what metal, what rate, put numbers to anything. Not that you could follow a procedure blindly and work in the nuclear industry, but the point is you have an idea of what success looks like.
Amount would, and in the worst cases, most of it would just get sucked out the bottom of the mold. But with that being said, my mold crisis was now apparently solved, and at this point,
that is so beautiful.
I was confident that I could actually do it with beryllium, and it was time to try making some metallic glass. So I went and got all of the metals that I would need for this, which, as I mentioned earlier, was zirconium, beryllium, titanium, copper, and nickel.
All in these nice little beads. I do appreciate the organization and the separation of things that have higher toxicity, like beryllium.
All of these were also the highest purity that I was able to find,
Wow.
and besides the beryllium, which was the lowest at 99.5% pure, all of the others were at least 99.9. But moving on, with all of these metals in hand, what I had to do next was measure them out and to get the exact amounts that I would need for that Vitroloi 1 recipe. I also decided to start out with the beryllium.
I can see how getting mostly pure just makes the math that much easier. Also, just not counting for impurities that can just make it more challenging to make a mold of anything.
Which was going to be a bit more difficult because it could only be handled in the fume hood. And when I felt that I was ready, I cracked open the bag. I then made sure to handle it as carefully as possible.
Now, is he wearing a mask? I know in the thumbnail he was, but just in addition to the fume hood, just to be extra careful, I guess we'll see.
So that any dust that was let off would be kept at a minimum, and I quickly found a piece that I liked.
That plastic bag, though, that's going to need to be disposed of after he's done, because it's all the little dust and particles that are going to get stuck on the plastic bag. That is one fairly common thing that is thrown away in contaminated areas and nuclear power plants, or various just types of plastic bags. Bags just have a tendency to get a lot of dust, particulate matter lumped into them. If you have a radioactive source that's loose, then yeah, the bag is considered nuclear waste at that point, albeit low-level stuff, the kind that you would keep on site. It's not like people are directly handling spent fuel.
I then gently placed it on the scale, and the goal here was to try and measure out exactly 1.34 grams. With such large chunks, this wasn't really going to be possible, but eventually I was able to get 1.348 grams, which was close enough.
Okay, good. He's not going to try to machine or cut up the beryllium just to get the exact right mass he's using. I'm not sure what the significance of 1.34 is yet, but that's just gonna make a big mess, even with the fume hood.
And I sealed it all in a vial. I then spent the next 20 minutes measuring out 5 more vials of the beryllium, which would give me a total of 6 separate attempts at making the metallic glass, and I felt that this would be more than enough.
Okay, using something like that, a sealed container that can more reliably be cleaned is better than the plastic bags.
This meant that at this point, I was done picking through all of the dusty beryllium, and what I had to do next was the extremely fun part, where I got to load the masses of these 6 samples into a fresh Excel sheet. From there, I was able to do a bunch of...
I like that. I'm gonna carefully load them into an Excel spreadsheet. It's like, okay, that's... You don't need to be qualified on anything to do that.
Calculations, where the first one was to convert all of the molar percentages in the recipe to mass percentages, and when I was eventually done several minutes later, I had the final amounts of each metal.
Like that beryllium is in bold, because that's the challenging one.
Was also essential to confirm was that the total mass of each run added up to around 40 grams, which would give me a volume of about 6.6 milliliters. This is because, as I mentioned earlier...
It's funny to see milliliters for something that's a solid. I mean, it makes sense because it's going to be a mold, but...
The amount of metal was very important, and at least based on the tin, I found that this was the ideal amount. But either way, with these numbers in hand, I ended up spending the next hour measuring out all of the other metals, which was honestly a lot more tedious than I thought. This was mostly just because there was a lot of them,
and
but
tiny
also
beads.
because I had to use bolt cutters to carefully shave off small amounts of the pellets to get to the exact measurements. Eventually, though, I was able to finish measuring everything out, where this was what I would be using for run 1, and I thought that it was kind of interesting to see it laid out like this. It was also kind of sad.
Looks like you're just laying out some beads ready to make some jewelry or something. Bouncy atomic jewelry, that is.
Satisfying to see the other 25 vials that I would be using for the rest of the runs, and at this point, I was almost ready to make some metallic glass. The only other thing that I still had to do was move the entire arc melter to my fume hood, which was honestly kind of a huge pain, and to also add a HEPA filter to this part here, which would trap any beryllium dust or vapor that might get pulled out by the pump. Also, while I was at it, I decided to add a two-way valve to the argon input at the top, which I should have done from the beginning, and I replaced the power supply with one that I'd found on Amazon, because the original one was kind of a piece of crap. With all of this in place, though, I was finally ready to try making some bouncy metal, and after months of preparation and waiting, I was very excited to say the least.
I remember during outages, one of the most common thing that plant operators had to deal with was welding receptacles tripping on overcurrent in the reactor containment building. This is deep in an outage, everything's shut down, the reactor is in a safe condition. Even at this point, the reactor's not in the containment building because it's defueled, and the old fuel is in the spent fuel pool, and the new fuel hasn't been loaded yet in this particular example. It's obviously not a nuclear concern, it's just welding on various maintenance projects that are going on within the reactor containment building. And yeah, I just remember getting a lot of calls about welding receptacles tripping, especially on night shift for some reason.
So I just immediately got started, and the first thing that I had to do was add all of the metals to the copper crucible, which you might have noticed was different than the one before. This is because I'd swapped out the one with the mold for this one that instead had a huge well in the center.
I like the big hunk of the beryllium.
And that would actually be able to hold all of the loose metal pellets.
Okay.
To a small well in the back, I also added a bunch of extra titanium pellets, which was very important, and I'll explain why in a bit. With everything loaded up, though, I then closed the chamber and I started clearing it from air, just like I'd done many times before, and while I was doing this, I kept the fume hood glass as low as possible. I had also hooked up the vacuum.
So he's not wearing a mask, though. I don't know. I've never worked with beryllium, but just considering how little it takes, and I don't know what grade of HEPA filter he's got there coming out of that exhaust, but I don't know if I trust it.
Pump to another foot pedal, and I moved the argon valve really close to the opening of the fume hood, which allowed me to do all of this while being completely protected.
You still got a gap there, and that filter looks like it goes slightly below that gap. Let's face it, there's risk with every job, and you're never completely protected. It's about reasonable ways to reduce risk. But where I worked, let's say this was a airborne radioactive contaminant, particulate matter, some level of additional respiratory protection would likely be required. It would be one thing if he was standing at, say, the opposite side of the lab, or if it was fully closed or something, but I don't know, man. I don't think you're going to talk me into doing this.
Right now, this was probably a bit overkill, but it wouldn't be later on, and to prevent any possible screw-ups, I decided to just do it like this every time the chamber had to be cleared. When I was eventually done, though, I was ready to start melting stuff, and I flipped on the new power supply. I then started blasting the titanium at the back, and this wasn't something that I had done before, but with the metallic glass, this was very important. This is because even though the argon that I was using was 99.999% pure,
999, okay.
it probably still contained a very small amount of moisture, carbon dioxide,
Sure.
and oxygen, which could all react with my metallic glass and potentially contaminate it. So I was of course going to have to do something to try and get rid of them, and thankfully this was supposed to be easy to do by just melting some titanium.
It's interesting that 0.001% could pose a problem when you're making something like this.
Except, unfortunately, I was going to have to do this every single time. With that being said, though, I was now finally ready to try combining all of the metals and to melt the scary beryllium, and I would be lying if I said that I wasn't at least a bit nervous. I was also kind of assuming that this
But not enough to wear a mask, even a N95 mask.
whole process would be relatively clean and nice, especially after melting the titanium, but I was almost immediately proven wrong. Right away, there was a bunch of smoke that was being let off, which
okay.
I thought was interesting, considering that the metals were supposed to be super pure. However, I assumed that it was probably just from some minor impurity, and I was hoping that it wouldn't get too much worse. Except it apparently did. I mean,
happened?
it really looked like the ball of beryllium had just exploded and released a whole bunch of toxic dust and smoke.
Dude, what? That's why you wear the respirator, man. What?
And this was definitely something that I did not like.
No.
This wasn't too surprising though, considering that the beryllium was the least pure metal out of them all, and I should say that despite all of this nasty smoke, I still felt that things were going okay. But anyway, what I
You felt that and that you weren't getting sick, or what?
had now was a really hot and kind of crusty looking blob of potentially metallic glass, and in an ideal world, this melting step would have now been done. Unfortunately though, the world that we live in is far from ideal, and in this case,
I'm glad he's showing
there was
this step,
probably
though.
still a bunch of unmelted metal at the bottom, which I was going to have to deal with using this convenient tool that was built into the machine. At least according to the manual, it was supposed to allow me to easily flip over the metal. However, I
weird
quickly
shit.
realized that this was going to be extremely frustrating.
So you got some gunk that you haven't identified. Beryllium was in the mixture, and now you're smacking it like I've seen on an Electroboom video. Okay.
After 5 minutes, though, I was eventually able to flip it, and on the bottom, it was possible to see the outline of all the pellets that clearly didn't
Check
melt.
that out.
And I just immediately started blasting it. It then all quickly started melting again and getting much more evenly mixed, and what was nice was that it didn't seem to let off nearly as much smoke. What was less nice, though, was that according to every source that I had read, to get a good uniform mixture of the metals, I was gonna have to flip it at least 3 more times.
You know, just like making a burger, a beryllium burger, with a weird shaped spatula.
This definitely wasn't ideal, but I also really didn't have a
Here he
choice.
is.
And when I was eventually done, over 20 minutes later, I had a nice blob of red hot metal.
I mean, look, I know it's contained, and the exhaust goes to a HEPA filter, so what I said earlier might be overly conservative, but it's what I'm used to as being overly conservative.
Now, all I had to do was just let it sit there and wait for it to cool down, and for the cold crucible to quickly pull away its heat. At the same time, though, I felt that it was a good idea to watch it very closely and to see exactly how long it took to solidify. This is because in general, when making metallic glass, getting it to freeze
Shinier.
as fast as possible was extremely important, and with the Vitrolloy 1, this was gonna have to happen in less than a few minutes.
So that's important for a few reasons. The rapid cooling, that is. You don't want any unwanted crystalline structures to form. I mean, the whole purpose of this is to have a more uniform structure that has its wonderful properties, such as high strength, corrosion resistance, and in the case of this video, extreme bounciness. And it can also just reduce your exposure time to the environment, less contamination, less oxidation, things of that nature.
This way, there wouldn't be enough time for any of the metal atoms to crystallize or to form any ordered structure before solidifying. Instead, at least in theory, they should all get locked in a random and amorphous state, and this is supposed to form a metal with very different properties that's commonly referred to as a metallic glass.
It's kind of an oxymoron having it be random and yet also uniform due to the lack of crystalline structures, but I get what he means.
With that being said, though, at this point, it looked like it had completely solidified, and considering that it had only taken about a minute, I was relatively confident that this was metallic glass, and that I now had a beautiful blob of bouncy metal. Before drawing any real conclusions, though, I was first going to have to get it out of this beryllium-riddled chamber, and with this setup, it was thankfully pretty easy. All I had to do was lower the glass as low as possible, and to pull out all of the dust by turning on the vacuum pump and trapping it in that little filter. I then refilled it with argon, and I repeated this cycle a few times, just to make sure that there was absolutely nothing left. After that, I flipped the two-way valve, which opened it to air and equalized the pressure, and now I was able to safely open it. So I carefully flipped up both of the clamps, and I slowly lifted the chamber to reveal my beautiful chunk of hopefully metallic glass. I then removed it from the crucible using some tongs, and I wiped it down with some wet paper towel to remove any toxic residues.
Just gonna put some paper towel on there. I mean, yeah, it works, but I can't say I've seen anyone pick up waste products with paper towels before at the nuclear plant, just because they have a tendency to fall apart.
And I took a closer look. What immediately stood out to me, though, and what honestly kind of surprised me, was that at least in this form, it didn't seem like it was anything super special. It really didn't feel any different than normal metal, and I mean, I know that I was holding it with tongs.
Here's some pure uranium metal. Looks pretty ordinary, doesn't it? You'd only see the green glowy stuff when exposed to UV light in the case of uranium.
But still, with a density somewhat similar to pure iron, it kind of just felt like one of those iron blobs that I'd made earlier. I of course couldn't just judge it by how it felt though, and I was gonna have to be a bit more scientific, and I was gonna have to do an actual test. So I went and got one of my ball bearings, which are normally used to just shoot from a slingshot, and when I dropped it, I was pleasantly surprised by what I saw.
Yeah?
I mean, it obviously wasn't even close to as good as what Steve Mold had, but it definitely seemed like it was abnormally bouncy, and I thought that it made a really interesting sound.
I mean, for something that shape, it does look bouncier than a rock.
There was something about it that just sounded springy to me, and I felt that this was a really good sign. To be absolutely sure that this was anything special, though, I of course had to compare it to some regular metal, and I decided to just use one of the blobs of iron. Then, all I had to do was drop the ball bearing, and I was honestly a bit worried that it would end up bouncing just as well, and that what I had made was actually trash, except it was almost laughably bad.
Yeah.
It wasn't even close to anything that I would say even resembled a bounce, and this told me that I was definitely on the right track.
Needs to create a bounciness scale.
At the same time, I also felt that turning what I had into a proper flat disc, and that giving it a solid base to sit on, would make it significantly bouncier, and that was of course what I had to try next.
Yeah.
Before moving on, though, I was first going to have to finish melting the 5 other runs that I had prepared, and I did my best to do this as fast
Thank you for putting on the added respiratory protection
as I could. However, despite this, it was still a very long and tedious process, and what made it even worse was that runs 3 and 6 apparently had beryllium that was even more explodey.
I can't with more exploding.
And it looked like the beryllium was sprayed everywhere. Dude. It also filled the entire chamber with so much smoke that it was almost impossible to see anything, and this was quite unfortunate to say the least. On the bright side, though, the other runs seemed to be totally normal and not even make that much smoke, And I also ended up seeing something that I thought was really interesting.
It's green.
More specifically, this was during run 4, when I had accidentally touched it before it had fully solidified, and this caused a small amount of it to get pulled away as a little string of goo.
Whoa.
And this wasn't like any other metal I had ever seen. In my opinion, it was a lot more like melted plastic or molten glass.
Contaminant?
And I felt that this was another really good sign that I had actually made metallic glass.
Okay.
But anyway, when I was eventually done 4 hours later, I had 6 beautiful blobs of metal, and I was feeling pretty hopeful. I also did a quick ball bearing test to confirm that they were all bouncy, and at least from this, they all seem to be about the same.
Okay.
Okay.
The only sad part was that when I weighed them all, the ones that were extra explodey had lost way too much mass, and this told me that most of the beryllium had probably just been sprayed around the chamber, and I wasn't going to be able to use them.
You're going to want to be careful cleaning that chamber out, too.
However, I didn't think that this was a huge issue, because even without them, I would still have 4 attempts to make the discs, and I felt that this was more than enough. With all that being said, though, at this point, it was getting really late, and I was completely exhausted, and I decided to come back to it the next day. When I returned in the morning, I was really motivated to get started, and the first thing that I did was swap out the crucible for the one with the mold. I then dropped in some fresh titanium, and onto the mold, I added the metallic glass that I'd made in the very first run.
Interesting.
After that, I closed everything up, quickly did all of the argon cyclings, and melted the titanium, and I was ready to go. So I just started blasting it using the same technique that I'd successfully used on the tin, and when I felt that it was hot enough, I carefully opened the vacuum to the mold. This then caused almost all of the metal to get quickly sucked in, only leaving behind a small bead at the top, and I was genuinely shocked that it had actually worked on my first try.
Whoa.
Okay.
So apparently, all of my practice had paid off, and now, inside the mold, there should have been a nice and hopefully perfect disc of metallic glass.
Let's see.
So, the only thing left to do was to get it out, and to do that, I quickly cycled it with the gas, and I flipped open the chamber. Then to release the mold, I added some screws, and with a makeshift piece of metal, I was able to carefully pull out the entire thing. With this in hand, the only thing left
Love that piece of metal has that exact purpose. That's hilarious.
to do was open it up, and inside of it, I was expecting to see a nice and beautiful disc, but I was immediately disappointed.
It's shiny.
This is because what I got instead was an
goo.
ugly piece of crap that somehow didn't even fill the entire mold, and what bothered me even more was that it seemed like it was pulled in very weirdly, which caused this gap to form in the middle.
Yeah.
On top of this, there was a lot of metal that was definitely getting sucked out the bottom, as evidenced by the tail, and what was also really bad was that it looked like even if the button at the top had gone into the mold, it would have only barely been able to fill it. Overall, this was a little sad to say the least, but
looks too sticky.
at the same time, I wasn't too worried because I, of course, still had a few more attempts, and I felt that they would be more than enough
Half of it left.
to succeed at least once. However, apparently, they were not, and while the next attempt was technically better, the one after that was an absolute disaster where almost all of the metal had gone right through the mold. This left me with only one last try, and at this point, I felt that it was pretty clear that I was going to have to do something different, so I decided to cut off some of the extra stuff from all of the failed attempts, which really did feel like trying to cut glass.
Holy.
I then combined all of it together, and I was hoping that with all of the extra metal,
That's a good idea. Form of reprocessing, recycling. Like what it would make sense to do with nuclear fuel, but we don't always do that. That's the subject of another video.
it would actually fill the mold, except it was the complete opposite, and I was never able to get any to go in. All that I ended up with was this huge and kind of useless chunk that I couldn't cut or break apart because of the beryllium.
Just get too sticky, too clogged.
And at this point, I couldn't help but feel pretty frustrated with how things were going. I mean, it was probably a bit naive to think that it was all just gonna magically work, especially because the vitrolloy had completely different properties than the tin, which probably required a different technique, and I had never even worked with it, but still. After all of these failed attempts, I couldn't help but kind of lose any faith that the mold was actually going to work or be remotely reliable, and I really did not have the motivation to spend another entire day measuring out all of the metals and then doing all of the melting and flipping, only for it to just probably fail again. Despite all of this though, there was still some hope, and I hadn't completely given up yet, because there was still one last thing that I had to try, which was that special 44mm well that I had mentioned earlier.
Okay.
I had made these just in case this exact scenario happened, where the mold completely let me down, and in my mind, they were so simple that there was no way they wouldn't
just stick it in there.
Work. However, long story short, it again ended up being a complete disappointment, and this is because it didn't at all spread out into a thin layer like I was hoping it would.
Yeah, you're not even using the whole...
And instead it just sat there as a ridiculously thick blob. I then just kind of said screw it, and I decided to keep adding metal until I got a full disc, which ended up taking all of the metal that I had, and when I was eventually done, I was left with this horrifically ugly monstrosity. Ooh. I mean, on the bright side, unlike all of the other attempts, it was actually a full disc, and there was part of me that wanted to just accept this as my final result and call it a day, but I knew deep down that it was complete trash. There was also no way for me to fix it without a ridiculous amount of grinding or machining, and it was at this point that I basically just gave up. Over the next few weeks, though, I couldn't stop thinking about it, even while I was working on other projects.
Mystery project.
And inevitably, I ended up with a bunch of ideas that I really wanted to try. For some reason...
Time you get ideas when you just take a break, you work on a completely different project, and then it just comes to you. This whole idea of taking a break, though, that was part of how nuclear fission was discovered. This was in 1938 when Otto Hahn and Fritz Strassmann were doing experiments just to create heavier elements via neutron bombardment, bombarding uranium with neutrons, expecting just to form heavier elements. And then after completing the experiments and reviewing their results over the Christmas holidays, they discovered barium in the samples, which is way lighter than anything they expected to happen when bombarding uranium with neutrons, and they realized that it had split into much smaller atoms. The same process that happens in nuclear power plants. So, yes, taking a break's a good idea.
And I was also feeling really confident that I could actually get the mold to work properly and consistently, and I decided to just jump right back into the project, and I started weighing out the metals. When you get the
idea, go for it.
This time, though, I was very careful to only choose the beryllium balls, and none of the shards, which seemed to be more explodey, and I also weighed out 30% more of everything.
Okay.
This is because I felt that 30% more metal would be the perfect amount, and that it would be just enough to compensate for all the metal that was getting shot out the bottom, while simultaneously not being so much that it would refuse to go into the mold.
Okay.
I'm not sure why, but I was also feeling weirdly optimistic, so I decided to only give myself 4 attempts, and with all of the metals ready, I did all of the same melting and flipping steps. When I was eventually done, I had these 4 beautiful blobs of metallic glass, which pretty much looked exactly the same as the ones from earlier, except they were 30% bigger, and I loaded the first
Maybe it's the size, that's why they looked better to me.
One onto the mold. I then did all of the typical gas cyclings and titanium melting, and after hours of tedious work, it was finally time to see if any of my new ideas were actually good,
close, I guess,
or if it would all end in another complete failure, and I just started blasting the metal. As usual, this caused it to all quickly melt, and now, The first major thing that I was going to do differently was to just keep blasting it for a ridiculous amount of time. This is because I found out that unlike normal metal, metallic glass is significantly worse at conducting heat, and it was very likely that it just took a lot longer for the entire thing to fully liquefy. So I decided to heat it for no...
Heat resistance is a good process of metallic glass, just like I mentioned earlier about the allowing transformers to operate at higher temperatures.
No less than a minute at near max power, and when I felt that it looked good, I moved the electrode to the middle, and I continued blasting it there for another 10 seconds. This would just really make sure that it was fully liquid above the hole, and then after that, the only thing left to do was open the vacuum valve. I also had to do this slowly and very carefully, which I felt would help prevent the metal from just blasting through the mold, and almost right away, it all started getting sucked in. Then not long after, it started looking very similar to my other attempts, where there was just a small bead left at the top. The only difference this time was that the bead looked like it was slightly bigger, which kind of implied that it didn't all go in, but at the same time, I did start with a lot more metal, which made it hard to tell. Either way, I then let it cool, cycled the gas, and popped it out, and part of me was mentally preparing for what was probably another miserable failure. However, that absolutely was not the case, and inside of the mold was what looked like a near-perfect disc.
Oh my god, it actually worked.
I mean, it still had some issues, but it was way nicer than any other attempt, and I really couldn't have asked for anything better.
Yes! Yes! That is good.
So clearly, getting the optimal amount of metal was very important, and just using a slightly different technique had apparently made a huge difference, and I was both extremely excited and relieved. With that being said, I then went ahead and did the exact same thing for all of the other ones, and a couple of them were still a bit finicky, but in the end, I was actually able to make 3 more discs. Like the first one though, none of them were quite perfect, and they all had some slight defects, and on the surface of them, they all looked like they had some weird ripples. However, from what I could tell, this was extremely minor, and it only seemed to be visible because they were so shiny, and overall, I still felt that they were more than good enough. But moving on, now that I actually had it in disc form, what I've...
Getting repeated results is important, so it sounds like he cracked the code, or at least somewhat.
Of course had to do next was test out my theory from earlier, and to see if it was bouncier. So I went and got my stainless steel base, which had been made by my friend Justin, who runs the channel The Thought Emporium, and he was able to machine it to the exact same dimensions as Steve's. I then carefully placed my disc on top of it, and I went and got my ball bearing, and for what felt like the millionth time, I was overcome with disappointment.
Is it because of all the
This is because
ripples?
Somehow it seemed to be only barely bouncy, and it was apparently even worse than that huge piece of trash that I had made earlier.
Yeah, that had
At
some
first,
bounces.
this kind of surprised me, and I started thinking that I probably just screwed up measuring or mixing the metals, but at the same time, I knew that something was off because of the sound that it was making. Every time the ball hit it, it was making a clinking sound instead of the bouncy one that I had heard earlier, and in my opinion, this had to be happening because the disc wasn't perfectly flat.
Yeah.
This was probably causing it to slightly pivot and to get slammed into the base every time it was hit, and it was very possible that this was absorbing enough energy to completely ruin the bounce. It also
Shape is important.
thankfully seemed like it was a relatively easy thing to fix, and the obvious answer was to just glue it down. Before I could do that though, I was first going to have to clean it up a bit by cutting off all of the extra stuff with some bolt cutters, and by shaving down the nubs with some wet sandpaper. I also had to very lightly sand down the side that I was gonna glue so that it would stick better, and I did make a bit of dust doing this.
I was gonna say, be careful with anything involving sanding and dusting, just because there's bits of beryllium in there.
But it was also completely unavoidable. When I eventually felt that it was looking good, though,
hopefully he was wearing a respirator, and hopefully he's cleaning that up when he did that step.
I shot a bunch of super glue onto the steel base, and I quickly squished on the disc. I also slid it around to make sure that everything was covered with glue, and I honestly did a pretty horrible job, and the glue is dripping everywhere. However, regardless of that,
That actually kind of reminds me of me as a kid playing with super glue to make Warhammer models. I was not very good.
I still felt that things were going pretty well, and after waiting a day for it to fully cure, I quickly cleaned it up. I then carefully slid some acrylic tubing over it, which I was able to find on eBay, and now it was time to see if the glue had magically fixed everything. So again, I went and got a ball bearing, and I nervously hovered it above the tube, and well, it did somehow magically fix everything. I mean, it definitely seemed like it was bouncing just like in Steve's video, and thankfully, it was no longer making that clinking sound. The new sound that it was making was definitely more bouncy, and it was much louder than I expected, and at this point, I was still genuinely surprised that it was actually working.
It actually works. That is...
Tapping so fast. Now this metallic glass could actually be used as, I guess, really expensive radiation shielding. Because in addition to simply containing beryllium, which, as I mentioned earlier, scatters neutrons, it has a more uniform density, which makes it effective at absorbing and attenuating radiation, such as gamma rays and neutrons, which are the hardest type to shield against, involving the most amount of heavier materials, such as lead in the case of gamma radiation, and lots of concrete in the case of neutron radiation. The obvious trade-off is this stuff is a lot harder to make, but conceivably, if you happen to have a lot of this stuff lying around, it can help. It also has high strength and corrosion resistance, which, coupled with the beryllium, would hold up better under long periods of times in a neutron field of a nuclear reactor, because it's much more resistant to neutron embrittlement. This corrosion-resistant material could also be used in nuclear waste containers, especially if you got a really hot source in there. But, I mean, it's not, but I'm just talking theoretically because it's cheaper to use large quantities of lead or concrete. But metallic glass does have some interesting properties that would be helpful in nuclear engineering. It's just expensive in an industry that already involves a lot of expensive materials.
Really cool.
I love that sound effect.
It's actually amazing. But with that being said, I was now super happy and relieved that the glue had worked, and at this point, there was only one thing still left to do, and that was to get all of the other discs onto a steel base. So I quickly cleaned them up, just like the first.
I thought it was going to be, have one disc on one side, one disc on the other, put it in a tube, and like shake it up really fast so it just goes bouncy, bouncy, bouncy a lot. That'd be cool, though.
One, and I glued each of them to a fresh steel cylinder that I'd made using a service called Protolabs Network. This gave me a total of 4 nice-looking little setups, and with all of the extra stuff that I had to cut off, I was actually able to make a 5th one. I then gave all of them their own tube, and now I was finally able to do what I dreamed of when I started this project, and I tested them all at the same time.
Oh, that's cool.
This was honestly mostly just for fun,
of course,
but I was also really curious to see if there would be any difference, and I wasn't surprised to see that there was. I mean, I think the metallic glass itself was mostly fine, and I think the main difference just came down to the quality of the disc surface.
Yeah.
For example, the third one had by far the crappiest surface, followed by the fourth, where both of them had little bumps and divots that I was hoping wouldn't be a problem, but they...
Smooth surfaces is such an important engineering principle. I mean, in nuclear engineering, it comes up in any type of heat exchanger, including the reactor coolant that exchanges with the steam generators. You want to maximize the amount of heat transfer. Having contaminants there, whether it be the tube side or the shell side, can result in lost efficiency and a lot of lost revenue. You also need smooth nuclear fuel cladding, which is a zirconium alloy. It's not a metallic glass, but having smooth surfaces just increase its strength, its temperature resistance. It reduces corrosion, likelihood of fouling, because remember, it's under very high pressure and very high temperatures. And you do not want your fuel cladding to get fouled, because that is the first fission product barrier to the public. If that gets fouled, you just run the risk of fission products breaching the cladding.
Consistently performed the worst. In theory, though, I think that this could all be easily fixed by just grinding and repolishing the surface, but as of right now, I don't really have a way to do that safely.
That's really it. If you're going to grind it that finely that you'd want to get rid of to have sub-micron level of smoothness, the proper word's escaping me right now, it's going to involve machining stuff that could kick up some beryllium dust.
At the same time, I'm also more than happy with numbers 1, 2, and 5, which seem to perform almost just as well as Steve's, and that's more than enough for me. This is because it allows me to keep one for myself, give one to Steve, which I promised I would do in a comment on his video, and to also give one away to you guys. If you want a chance to get it, there are also no real requirements, and you don't need to subscribe or comment or do anything like that. All you need to do is send a nice email to giveaway at nilered.ca, and after a week, I'll have the winner randomly picked. And just as a point of safety, because I don't think I said it in the video, the metallic glass in this disc form is totally safe, as long as you don't break it apart or try to sand it or grind it. But with that being said, in the end, this project turned out to be a lot trickier than I thought, especially with the whole mold setup.
Anything where you need that level of
perfection. It actually worked out. What's also nice is that it gave me a huge interest in metallic glass in general, and I plan to do some more videos on it in the future.
Cool.
For now, though, I think I'm done working with nasty and toxic beryllium, and I'm gonna try focusing on some even more dangerous projects, like making nuclear-powered glow toys.
Is that supposed to be radium? Oh, no, no. And it's a little baby, like the little baby you get in the Mardi Gras king cake that can get eaten. Oh, no, we don't want to relive the radium girls. Now, if there's a way he could do it safely, I'll look forward to that, but the way he phrased that, I really hope he knows what he's doing. I mean, as long as you don't eat it and use a very small amount of radium, and limit your exposure time, you can make it reasonably safe in a highly controlled environment. But, oh man. But hey, I would be happy to watch it and offer insight when he does it. I really enjoy watching his videos. Thank you very much for watching. I'll see you next time.